Hello and welcome to the enhancement session on balancing simple equations. This session will go over any misconceptions on balancing simple equations but also word equations, chemical reactions taking place, how to detect them, and also physical and chemical changes, the difference between them. So the first key definition is for physical changes, and these are reversible. This means it can be changed back to its original form, and most common example is being from ice to water. So ice can be melted at a higher temperature, often above 0 degrees Celsius, to liquid form, but because its chemical structure hasn't been changed, it means water, as if you put it in a freezer, can be frozen if it goes below that, so it can go back to ice. And this is a reversible change because we can do it as many times as you want, going from ice to water, water to ice, also from water to a gas, so steam. Chemical changes, on the other hand, are irreversible, so this means it cannot be changed back to its original form, and this means it is a permanent change. So the common example, the first one, is if you crack an egg and fry an egg, it means you cannot get it, once you've cooked that egg, you cannot get it back to its original form within the eggshell. And a second example is if you've ever been camping and burned some wood out of a fire, that wood can not be made back into its original form. It can be converted into charred wood and a gas. That means its chemical composition has been changed, it is irreversible, and it cannot be made back into its original change. So it is a permanent change. So, how can we tell a chemical reaction has taken place in an experiment? We can tell a chemical reaction has taken place by what we see, hear, or smell. So we detect that there is a chemical reaction taking place. And I'm going to go over these few examples now. So, the first one will be bubbles produced in a test tube to show gas is being produced and is escaping. And also smoke. This can be seen by carbon dioxide escaping from the test tube there. Also, another example being an odor detected, so you can smell an odor being produced, and that's also a gas. Another example being a change in color. So we have a strong acid there, which is detected by red on the pH scale, and a yellow next to it, which is a weak acid on the pH scale. Next example would be a change in temperature. So an exothermic reaction increases temperature, and an endothermic reaction decreases temperature. And a final example, the common example, is you can hear a gas being escaping, hear a noise, such as the hydrogen test, which is a squeaky pop test as well. Before we go into balancing equations, we need to take a step back and go on to understanding word equations. So, got two examples here of two different word equations. Got carbon plus oxygen makes carbon dioxide, simple one there. The more challenging one here, calcium plus nitric acid is calcium nitrate plus hydrogen. So, we need to understand what each symbol means and also what's the difference between reactants and products. That's a key misconception. So, reactants are always the ones that come before the arrow because they are reacting together. Very simple, they are reacting together, so they are reactants. Whereas the products are what is produced after the reactants have reacted together. It comes after the arrow. It shows that a chemical reaction, a reaction has taken place and a new product has been formed. Now, word equations do not need to be balanced because it is only the words, it is not the symbols. Whereas symbol equations use elements from the periodic table as the symbols. So all elements on the periodic table are found here, with the metals being shown in the red and the non-metals being shown in the yellow here. They're found on the periodic table as shown. Now, balancing symbol equations is not an easy task. It is quite difficult, and it takes a thorough amount of practice and repeated exercises. So the first example shows you reaction of Mg, which is magnesium, plus O2, which is oxygen, and that makes MgO, which is magnesium oxide. So at the moment, because these are unbalanced, we have to set out a simple structure like this. This is the easiest way for me personally how to balance equations. So I started off by listing each different element. So we've got magnesium and oxygen on that side, magnesium and oxygen on this side, and it comes after the arrow, remember, because that's when the reaction is taking place to show there's been a change, a chemical reaction. So, and we count up how many of each element there is. So there's one magnesium there, we write down one magnesium on this side. But here we have two, so we write down two oxygens on this side. After the arrow though, you can see there's, even though there's the same number of magnesiums, there is a different number, there's only one oxygen. So we need to change this. The first key rule of balancing symbol equations is that we cannot put numbers after the compounds. We cannot put O2 at the end here because it would actually change the structure of MgO to something different, which is not what we got. So we can only put numbers in front of the actual elements themselves. So we can only put it in front of it. But we can change that as many times as we want. So as I said, stated there, the example, so we've got one oxygen there and two there. So it means we have to put a 2, change that to a 2. So because we can't put O2 there, we have to put a 2 in front of the MgO here, like so. And that means we have changed O to the 2 there on this side. That means these two are now balanced. But because 2 MgO, that means everything after the 2 is times by 2. So we now have 2 magnesiums, which is not what we want. So we're now unbalanced on this side. So therefore, we have to go back on this side and put a 2 in front of the magnesium on this side to balance it out. There we go, just like that. That means we are now balanced on this side. So we've got 2 Mgs there, 2 oxygens there, 2 Mgs there, and 2 Os there. Now, example 2 looks a lot trickier, but actually if you follow the same structure, it's just actually as easy. So, we've got CH4 plus Cl2, so that's methane plus chlorine, makes calcium chloride plus hydrochloric acid. And so we've outlined all the, done the same structure, we've outlined all the elements on this side. So we've got carbon, and there's 1 of them, hydrogen, there's 4 of them, and Cl was chlorine, and that means there's 2 of them because it's followed by the 2 here. On this side, however, there's still 1 carbon, so that means it's the same number of carbons, but there is only 1 hydrogen just here, and there's actually 5 chlorine, so 4 there, and then there's 1 at the end there. So we need to change this. The first thing we need to do actually is now to balance the hydrogens first. So as we can see on this side, we've only got 1, but on the left hand side we have 4. So we've got 4 hydrogens there and only 1. So that means on this side we need to add a 4 to the start of the HCl there, like so. That means we have now changed the number of hydrogens from 1 to 4 on this side. So that means they are now balanced. So it's 4 there and 4 hydrogens there. However, we have now changed the number of chlorines from 5 to now 8, because we've got 4 on this side and it was only 1, but now we've added 3 more to make it 4 on this side. 4 and 4 means there are 8 chlorines. So what we need to change that by that, so the 2 numbers that go into common here, so 2 and 8, what goes in common, it'd be 4. So that means on this side we'd have to put a 4 in front of the Cl2 here to make sure it can get to 8, because 4 times 2 would be 8, like so. And that means we have now successfully changed that chlorine from 4 to 8. We've doubled it, and that means we are now completely balanced. So this is the balanced symbol equation. We didn't have to change any of the carbons. We changed the hydrogens from 1 to 4 there by adding a 4 here on the HCl. And we also did the same because the numbers are common between 2 and 8, it'd be 4. And we added a 4 to HCl, Cl2 there. Now, balancing equations is not an easy task, and it does take lots of practice. And practice is what we're going to go over now. So, try and balance the following equations here, following symbol equations 1, 2, and 3. Pause the video, have a go, and this will take time. So give yourself 5 minutes, and then unpause the video once you have finished. Now, hope you finished that and had a good go with that, using the same structure as outlined before. So making sure you put a line where the arrow is and outline the number of elements on each side, and then try and balance them, the numbers, by putting each number in front. So you should have got examples like this. So you have 2 CO, so you add a 2 there and a 2 there, just to balance the coppers, because oxygen is already 2 there. On this side, you only had to add a 2 in front of the HCl because the Z's zincs were already balanced. And on this side, you had to add a 2 in front of sodium, the water, and the sodium hydroxide here, so 2 in there. Give yourself a mark out of 3, and that completes the structure. We have now finished the supplementary session on how to balance simple equations, but this has not finished. Remember, this takes time and practice, and using the same structure, you can balance any simple equation no matter how hard, as long as you use the simple structure of putting a line underneath the arrow and outlining how many elements there are on each side. It takes time, it takes practice, and best of luck.